My name's Luke,
And my name's Kyle.
and this is our 3 resistor circuit video. Okay, so we have a couple different objectives for this lab. The first one is to be able to do everything in theory on pen and paper first. The second one is to be able to put it into a simulation, which we're going to be using LT-SPICE later on. And the third objective is to be able to do it in the lab. So the first objective is to do it on pen and paper, which we have a great explanation done by Kyle.
We have a circuit with a 5-volt power source and 3 resistors in series with 100 ohm resistance each. An equivalent circuit would have one resistor with 300 ohms by adding all the 100 ohm resistors from the previous circuit. There should be a 5-volt drop across the 300 ohms. Using V equals IR, we can get that current equals voltage divided by resistance. So we have 5 volts divided by 300 ohms, which equals 0.0167 amps across all resistors. Current is shared with resistors in series. Using V equals IR again, we can determine that the voltage drop across each resistor is given by 0.0167 times 100, which equals 1.67 volt. Voltage drops across each resistor. So we need to find the current that flows through the equivalent circuit, given by this equation. So you get 0.033 amps flowing through the circuit. Now we need to find the voltage drop across these two resistors, given by V equals IR. So across the 50 ohm resistor, you get 1.65 volt drop, and across the 100 ohm resistor, you get a 3.3 volt drop. And to find the current flowing through the parallel resistors, we use I of 1.65 over 100, which is 0.0165 A current flowing through each. Find the current flowing through the last two parallel resistors is given by equation 5 volts over 100 ohms, also equals 0.05 amps. So the current of 0.05 amps flows through each parallel resistor, and 5 volts flows across each resistor. So we have 3 parallel resistors with a 5 volt power supply. Each resistor has a resistance of 100 ohms. To find the equivalent circuit, we use this equation to get 33.3 ohms, and the equivalent circuit is here. We now have a circuit with another 5 volt power supply and 2 resistors in parallel, and the last one being in series, each have a resistance of 100 ohms. To determine an equivalent resistor for the parallel resistors, we need to use this equation, which will give you 50 ohms. And there's the equivalent resistor for the parallel resistor. Next, we add up these 2 resistors to get an equivalent circuit that looks like this. The former circuit has 2 resistors in series, and the final one being parallel to those, and the equivalent circuit would look like this. After all the math is done, the current going here is 0.075 amps, going down here is 0.025 amps, the voltage drop of 2.5 volts across this resistor, and the same for this resistor. The current going through this resistor is 0.05 amps, and the voltage drop should be 5 volts.
So we're now in LT-SPICE on the computer. Here's our first simple circuit where we have a power supply of 5 volts and 3 100 ohm resistors. We're just going to run this guy to get some numbers here so we can show it. Alright, so in a series circuit, like Kyle explained before, the current is going to be the same all the way across this circuit, which it would be the equivalency if we combined all 3 of these resistors. So I'm going to build that circuit right now, and I'll be right back. And good to go with our second circuit. It's all the way over here. I had the first one built and then ended up deleting it, but we'll look past that. So if we run this guy, we still get the same voltage at 5, and we're still gonna end up getting that 0.016 repeating. It basically concludes that if we were to add up all the resistors to total 300, it would still share the same current across the system. So next thing that we got to do is build a simple parallel circuit, which I will get to right now. So here we have a simple parallel circuit where we have 300 ohm resistors wired up in parallel, and I already built this guy so we can run it. And like Kaale was saying in the pen and paper video, that we have 5 volts across the entire system, and each resistor across it is going to have a current of 0.05 amps. After you do a simple math, conveniently have a calculator right here, of 5 volts over 100. So you get 0.05 across each. Alright, so here's our third circuit, which is again 5 volt power supply running to 2 100 ohm resistors that are wired in parallel, coming down to a resistor that is in series. We find that it acts almost like the last 2 circuits combined that we did. The voltage drop across the 2 that are wired in parallel is going to be 3.33, which again was stated in the pen and paper example. R1 and R2 is going to be again that 0.0167 amps. But when we get down to the one in series, the current is actually going to be more. So if you ended up doing the math, you would end up getting the corresponding circuits with the correct amperage that we have displayed right here. Here's our last circuit with 2 resistors wired in series that is wired in parallel with a separate resistor by itself. We find that there's a 2.5 volt drop across all of the resistors. So if you end up repeating the math that Kaale ended up doing before, we get 0.25 amps of current going to the 2 that are wired in series, and 0.5 going to our single resistor that is over here by itself. Alright, so in conclusion, with doing everything in a simulation like LT Spice, we find that all of the numbers line up compared to our answers that we ended up getting on paper. So the only step that is left at this point is to be able to do it in the real world. So here we are in lab. This is a quick measurement that we took across the entire circuit. We ended up doing just a simple series circuit to start off. That's all we had time for, really. Here's a quick picture of our circuit itself. The red wire coming in is our positive, and then goes from one resistor to the next, and then back to the power supply through the white wire. So what we were doing here is we were actually measuring the voltage drop across the second resistor in the system. Remember about probably 6 minutes ago when Kaale was doing all that math, it turned out that that was the voltage drop that we calculated from the first equations. The short clip is how we ended up measuring current. We actually had to break the circuit, and we ended up getting 16.4. That 16.4 is in milliamps, so if you actually do the conversion, you actually get 0.0164 as your current going through that point in the system. So again, the numbers lined up. That pretty much concludes our 3 resistor circuit video. We ended up achieving the 3 objectives. We did it on pen and paper, a simulation, and we do have the numbers in the real world. So thanks for watching. We really appreciate your time, and we'll see you next time.